frequency polygon. Frequency polygon is a line graph. It's a line that emphasizes the continuous change, which is the line is a continuous line. There's no gap. There's no discontinuity. And they are done with the class midpoint on the horizontal axis. So polygon has a 3 characteristics. Number one, they are a line graph. Number 2, the line is a continuous line. Number 3, they use a midpoint as a horizontal axis. So we look at the table here. This table is the same example. We take the midpoint and we find the frequency of each class, right? Now we want to transfer this data, this table, into the graph. Look at the note here. The bar graph should have a begin and end point on the horizontal axis. So extend the left side to one class width before the first class midpoint, and extend the right side to one class width after the last class midpoint. So with a polygon, we need to find the begin point and the end point. Both of these 2 points, they intersect with the x-axis. Now, how do we find the begin point and the end point? So this is the midpoint, right? So here we need to find begin point. And then we need to find the end point here. End midpoint and the begin midpoint. Now, if you subtract the 2 midpoint here, this is the same distance like class width, which is 36. When you subtract these 2, you get 36 as well. When you subtract these 2, you get 36, which is finding the end midpoint. I just continue to add 36. Then I will find the end point of the midpoint. Finding the begin midpoint, I simply take the 172 to subtract 36. Then I will find the midpoint. On the begin point. So look at the graph here. The begin point, they take the 136.5 because when we take the 172.5 to subtract 36, we will get a 136.5. So this point is a begin point. The last class midpoint is a 388.5. When we add 36, we will get 424.5. So this number will turn to the last midpoint on the polygon. And these 2 points always intersect with x-axis. So this is a polygon. It's a line graph. There's no gap. It has they take the midpoint of the x-axis scale. It comes with the end point, and the begin point. So this is a polygon. Talk about relative frequency. Now, relative frequency is a ratio, right? It's a ratio between the frequency of each class level to compare with the total frequency. That is the relative frequency. The differences between relative frequency and the frequency, only the vertical axis differences. When we take the frequency to display the graph, your vertical axis that represent the frequency. So your vertical bar has a number, it's a counting number, the size of your data, right? So it's from 1, 2, 3, 4, 5, 6, or up to the largest size of your data. This is the frequency. Cumulative frequency is a proportion, is a ratio, is a percentage. So on your relative frequency graph, your vertical axis, they are the decimal. Most of case we see the decimal because they are the ratio that represent each category, the frequency to compare the total sum frequency. So just a presentation with a numerical number differences. However, the graph, your relative frequency graph should look very similar to your frequency graph because they have the same pattern, they have the same shape, they have the same spread. Because your data, they are exactly the same. We just take a different scale. So relative frequency should have the very similar, eventually they are the same. They are the same graph, but just kind of like this one, they will zoom in, right? It will shrink. We squeeze, right? We make the scale turn to small scale, so your graph will tend to go a little bit flat. When you compare with the frequency histogram graph, right? This is more shrink, and this is more flat. So that's the only differences. Another type of frequency we call cumulative frequency. Cumulative frequency, we just take the frequency of that class to add all the previous frequency. It's just like when we have the final exam, we call that the cumulative exam. Why is that? Because we add the material from the first exam combined with the second exam combined with the third exam. So all the resource, everything go to the final exam. So that would be the cumulative. So same idea here. When we have a cumulative frequency, we just continue to add a number from the previous frequency number. Most of the time, when we need a cumulative frequency because we want to construct the Ogive graph, which is the cumulative frequency graph. They are the same. Just give the different name to call it. Now construct the relative Ogive graph. We need to find the cumulative frequency number. And then you have to specify the horizontal and the vertical scale. And then you plot the point and that represent the upper class boundary. So here they take the upper class boundary on the horizontal axis. And then you connect all the points. Use a line to connect all the points. And then the graph should start at the lower boundary and then just keep going up. So the Ogive graph is a keep going up graph and never go down. It will just keep going up. So we look at the table here. So the first column, they represent the upper class boundary. So upper class boundary getting from our previous data, they are all the upper boundary. We have the frequency. In order to construct the Ogive, we need to find the cumulative frequency. So the cumulative frequency is getting from, we take the 3 because that's the first class frequency, right? Now, on the next class, finding the cumulative frequency, we simply to add a 3 with 2. So the cumulative frequency on the second class is 10 to the 5. And then you continue to use the 5 to add with 5, you'll get a 10. And you just continue to do the same structure, same calculation. Now keep in mind, the last class cumulative frequency number must equal the total size of the frequency. We look at the graph. So this is a Ogive graph. On the vertical axis, they label the cumulative frequency. So you should know this is Ogive graph. It's a keep going up graph. On the horizontal axis, they use the upper boundary, right? So the upper boundary start from 154.5 And then we have upper boundary is 190.5. So label those points, upper boundary, and then you label the cumulative frequency. It starts from 3, right? 190.5, that's the upper boundary of the first class. The cumulative number was 3. And then the next upper boundary is 226.5. And 226.5, when we have 3 plus 5, we here, oh sorry, it's 3 plus 2, we get a 5, right? So the upper boundary of the second class is 226.5. Cumulative frequency number was 5. So we just continue to structure the cumulative frequency versus with the upper boundary. Here, same way, we need to find the begin point. This begin point, same way, when I subtract from 36, which is class limit. So you see class limit is very useful. With this number, we treat each interval equally likely chance, right? Everybody subtract 36 or everybody plus 36, so no argument. So when I subtract 36 from 190.5, I get 154.5. So this point will turn to the begin point. This is a begin point. Ogive graph, there's no need to find a endpoint because the endpoint will not intersect with the x-axis. Interpreting the histogram and the distribution shape. Now, these two graphs, they look very symmetrical, right? But the differences between A and B is A, they have the symmetric pattern, which is if I draw the middle line that represents the middle graph here, if you look at the both ends of the bar graph, they are exactly the same. So this one we call the mount shape, which is this one is equal to this one because they have the same y value. These two, they have the same y value, right? And these two, they have the same y value. So they are the mount shape. It's perfect, exactly the same on both sides. If you treat the center as a middle line. So when you fold, if you treat here as a middle line, when you fold the graph into half and half, then these two graphs, they will exactly match. This is pretty much a symmetric graph as well, but here the right hand side bar graph is not exactly the same to the right hand side bar graph, right? They have the different frequency value, but this one we call bell shape. Most of the time we have the normal distribution graph like this because you barely to get a mount shape graph, and we don't like the graph like this because there's not too much information you can analyze it. Okay, most of case real world we see the graph like this, so we call bell shape, but both of them we call them normally distributed. Okay, this one, they all have the same y value, so this is a uniform. Because the y value, they have exactly the same. Whatever input you provide, they all have the same behavior. So nothing you can change, right? There's nothing you can analyze. Most of the case, we have the graph like this. You can see the tail kind of like skews to the left. So we call this a skew left graph. The reason caused the skew left graph because the outlier. The outlier make the change. It skews the average to the left. So outlier is kind of the troublemaker. We want to prevent the outlier, or when we analyze the data, we sometimes we have to exclude the outlier. Why? Because we cannot just because the single number, single data make the big differences and totally rule out the result we have. All right. Sometimes we have to label the error. Sometimes we call this as error. We just label, describe it. We don't consider this as this data as a data because it's not. This is not a good, reasonable presentation when we want to present our test result to satisfy most of people, right? We are looking for the middle region here. So the outlier, sometimes we have to exclude it. But we have the many different techniques to describe this data. But here, so far you just need to know, we call this a skew lab. Why it calls a skew lab? Because the outlier. This is a skew right. You can see the tail go to the right. So this is a skewed right graph or skew right histogram. Okay. Now this one is pretty much the unimodel, right? This is kind of like symmetric, normally distributed. And this one only has one peak, which is here's the mode. All right, so this is unimodel. Sometimes you might see the graph has two peaks. So we call this as a bimodel. With a bimodel, most of the case, you have the two different population inside of your data. But because this is a one population, this is another population. So with each population, they have their own mode. They have their own mean and the median. So that's why it has bimodel histogram. Alright, so here's a pretty much of your 2.1. We will talk about more skew graph, skew left, skew right here. Now with the skew left, the high peak here, they represent the mode. Because skew left, the average got pushed to the left, so the average, which is the mean, it turned to the most left-hand side. Alright, it just pushed to the left. Now between mode and mean, this would be the median, the middle point. When you have the skew left histogram or skew left data. When you have the skew right data, same way, the highest peak here, that is your mode. The mean got pushed to the right because of the outlier, right? Outlier here, so it just pushed the average, make the average turn to the super large because the outlier is very large number. So here is your mean, which is the average. The middle would be your median. So we will discuss more detail about the skew left, skew right, and we are going to talk about mode, median, and the mean on 2.3. So this is 2.1. So please move on to Math Lab assignment. And in the lesson module, there's a StatCrunch video. It has a video you can watch, and you can use the StatCrunch to play the game. It also has another resource that led you to get more information on 2.1. If you have any question, when we go back to class, feel free to let me know.